Tonight, we travel to a star, a single star, far from here. So far that the light reaching your eyes from it left long before your grandparents were born, before the pyramids, before the first written word. Its name is Stephenson 218, a quiet, technical name for one of the strangest objects in our galaxy. It is, by most measurements, the largest star ever discovered. How large? Larger than our entire solar system. If we placed it where our sun now sits, it would swallow Mercury, Venus, Earth, and Mars. It would reach past Jupiter. It would stretch almost to Saturn. A single star, as wide as an orbit. Welcome to Sleeping Galaxy. Tonight, we will drift slowly toward this giant. We will trace how it was found, hidden behind clouds of cosmic dust. We will travel inside its cool, vast atmosphere, so thin in places that it would feel almost like nothing at all. We will look at the strange paradox that surrounds it, that it is, perhaps, too large to exist. And we will sit quietly with the question that astronomers themselves cannot yet answer: whether Stephenson 218 is truly the largest, or whether the cosmos still has greater giants waiting to be found. This is the second part of our journey through the largest things in the universe. A series for the quiet hours, a series for falling asleep. So close your eyes if you wish, or look up if you can. The night is long, the cosmos is patient, and tonight we travel to a star. The first thing to understand about Stephenson 218 is that, for most of human history, no one could see it. It sits behind a curtain. That curtain is made of dust, cosmic dust, tiny grains of silicate, of carbon, of frozen ice, drifting between the stars. The dust does not seem like much when you imagine each grain, but there is a great deal of it in the inner regions of our galaxy. Enough to absorb almost all of the visible light coming through. Look toward the constellation Scutum tonight, a small, faint shape low in the summer sky for those of us in the northern hemisphere. Look at the soft, milky band of the Milky Way passing through it. Behind that band, beyond the dust, hidden from our eyes for thousands of years, sits a cluster of dying giants. But for a long time, we did not know they were there. In the 1960s and 70s, astronomers began to suspect that something was missing from their picture of the galaxy. Infrared light, light too red for human eyes to see, was leaking through the dust, and carrying with it stories that visible light could not tell. In the year 1983, a satellite was launched, the Infrared Astronomical Satellite, IRAS for short. It saw the sky in heat, in the long, gentle wavelengths that pierce through cosmic dust. What it saw, looking toward Scutum, was a great many bright sources, sources that had no name, sources that did not appear on any visible light map. 7 years later, in 1990, an American astronomer named Charles Bruce Stephenson was studying that infrared data. He noticed something, a cluster of unusually bright objects in a single small region of the sky. A cluster that, in visible light, did not exist. He gave it a name, Stephenson 2, the second of several such clusters he would identify. It would take another 17 years before anyone realized just how special this cluster was. In 2007, a team of astronomers, Davies, Feiger, Kudrytski, and others, looked more carefully. They found 26 red supergiants sitting close together, stars near the end of their lives, stars that had once been 10, 20, perhaps 30 times the mass of our Sun. Stars that had now grown so vast, so cool, so red, that they had become some of the largest objects in the Milky Way. It was, and remains, one of the densest groupings of red supergiants ever found. A graveyard of giants. A quiet corner of our galaxy where the largest stars come, in their final centuries, to die. And one star in the cluster, or perhaps just near it, was brighter than all the others. At first, in 2007, it was simply called Star 1. It was so bright, so unusual, that the astronomers were not sure it even belonged to the cluster. Its motion through space seemed slightly different. Its light slightly off. 3 years later, in 2010, a Japanese astronomer named Shuji Deguchi reclassified it. He gave it the name we use today, Stephenson 2-18, the 18th star, by his counting, in the wider region of the cluster. For a brief time, it was just another red supergiant, large, certainly, distant, mostly forgotten. And then, in 2012, came the measurement that changed everything. A team using new infrared observations calculated its size. The number they came up with was so large that, at first, it seemed impossible. 2,150 times the radius of our Sun. Larger than any star previously known. Larger than UY Scuti. Larger than VY Canis Majoris. Larger than WOH G64. Larger by a wide margin than anything anyone had ever measured. The largest star in the known universe. That, at least, was what the headline said. But the truth, as we shall see, is a little more uncertain, a little more interesting. Because the more closely astronomers looked at Stephenson 2-18, the more they began to question whether the measurement, large as it was, could really be trusted. For now, though, let us simply sit with the number. 2,150 times the size of the Sun. A star so vast that the very orbits of planets could rest within it. A star found by accident by a man looking for warm sources in a cold infrared sky. A whisper in the dust. A giant hidden in the dark.
2,150. That is the number. 2,150 times the radius of our Sun. It is, on its own, just a number, a long string of digits. And it is hard sometimes for the human mind to feel a number that large. So let us try, slowly, to understand it. Begin with the Sun. The Sun, which seems so vast to us, is roughly 1,390,000 kilometers across. You could fit about 109 Earths side by side along its diameter. Already, this is hard to imagine. The Sun is so large that it contains more than 99% of the mass of the entire solar system. Every planet, every moon, every asteroid, all of them combined make up less than 1%. That is the Sun. Now imagine a sphere 2,150 times wider than that. Place that sphere where the Sun now sits. The Sun's surface in our solar system reaches only a small distance into space. It does not even come close to the orbit of Mercury, the closest planet. But Stephenson 218, if it stood in the Sun's place, would not stop at Mercury. It would not stop at Venus. It would not stop at Earth. It would not stop at Mars. It would pass the asteroid belt, the gentle ring of small worlds between the inner and outer solar system. It would swallow Jupiter, the great king of our planets, and it would stretch almost to the orbit of Saturn, a single star as wide as the planetary orbits of an entire solar system. If you were standing on what we used to call Earth, though Earth would no longer exist, you would not look up to see a sun in the sky. You would simply be inside the sun, surrounded by it. The whole sky in every direction would be a soft, cool, red glow. There would be no sky. There would only be star. Let us try another way of feeling this. Imagine a beam of light, the fastest thing in the universe. Light travels at 300,000 kilometers every second. It is so fast that it can circle the entire Earth in less than 1/10 of a second. To go all the way around the surface of our Sun, that beam of light needs about 14.5 seconds. Already, this is strange to imagine. 14 seconds to circle a star. But 14 seconds is short. It is the length of a slow, deep breath. Now ask the same question of Stephenson 218. How long would light take to circle this star? Not seconds, not minutes, 9 hours. 9 full hours of a beam of light, traveling at the fastest speed possible in our universe just to make one slow loop around the outside of a single star. You could fall asleep and wake again, and the light would still be traveling. By volume, by the simple amount of space the star takes up, Stephenson 218 is roughly 10 billion times larger than our Sun. 10 billion. If our Sun were a single grain of dust, Stephenson 218 would be the size of a basketball. If our Sun were a small pebble, Stephenson 218 would be the size of a small mountain. And yet, and this is one of the strangest things about it, Stephenson 218 is not especially heavy. The Sun, for all its smaller size, contains a tremendous amount of matter packed tightly together. Stephenson 218, despite being 10 billion times the volume, contains only, at most, 30 or 40 times the Sun's mass. Maybe fewer by now. It has been losing material for a long, long time. This means it is far less dense than the Sun, less dense than air, less dense in its outer layers than the thin atmosphere on top of the highest mountains on Earth. If you could place your hand inside the outer layers of Stephenson 218, which you could not, of course, for many reasons, you might feel almost nothing at all. A soft, warm hush. The faintest breath of glowing gas. A star, in some places, lighter than a whisper. This is what we mean when we say red supergiant. Vast, cool, quiet, mostly empty. And so this is the picture. a star you could not see with your eyes, a star sitting 19,000 light-years away behind a curtain of dust, a star wide enough to contain Mercury, Venus, Earth, Mars, Jupiter, and almost Saturn, a star around which light itself takes 9 slow hours to travel, a star at the edge of what we thought was possible. But of course, the strange thing about edges is that nature does not always tell us where they are, and it would not be long before astronomers began to wonder, gently, quietly, whether this measurement, so large and so striking, could really be correct at all. If you could travel to Stephenson 218, and if your ship could somehow survive the journey, the strangest part might be how gentle it feels. You would expect heat, roaring fire, the violent surface of a sun. But Stephenson 218 is not the sun. It is a red supergiant. And red supergiants, despite their enormous size, are among the coolest stars in the sky. The sun's surface burns at about 5,800 degrees Kelvin, hot enough to glow yellow, hot enough that if you stood close to it, you would not last a single moment. Stephenson 218, by comparison, burns at only 3,200 degrees Kelvin, about half the temperature of our sun. That is why it is red rather than yellow. Cooler stars glow red, hotter stars glow blue, and the very largest stars, these vast, bloated supergiants, are almost always cool, almost always red. There is a reason for this. Let us approach it gently. A star, throughout its life, is a balance, a long, slow argument between two forces. On the inside, deep at the core, hydrogen and helium are being crushed together. They release energy. They push outward, pressing against the layers above them. This outward pressure wants to make the star expand. On the outside, the star's own gravity wants to pull everything inward, to collapse, to make the star smaller, denser, hotter. For most of a star's life, these two forces balance, the push and the pull, the outward and the inward, like a great patient breath held for billions of years. But near the end of a star's life, when the hydrogen at its core begins to run out, the balance changes. The core contracts. The outer layers, paradoxically, swell outward. The star grows and cools as it grows. The same amount of light spread across a much larger surface is no longer as concentrated. The color drifts from yellow toward orange, from orange toward red. This is what has happened to Stephenson 218. This is what is happening right now to many of its neighbors in the Stephenson 2 cluster. They are old. They have spent most of the fuel they were born with, and in their final great breath outward, they have become some of the largest things in the galaxy. But there is something strange about being so large. A star like our sun has a clear surface, a place where the dense, glowing interior ends and the thin corona begins. The transition is reasonably sharp. You could, in theory, draw a line. Stephenson 218 has no such line. Its outer layers are so distended, so puffed out, that the boundary becomes uncertain. The gas thins gradually. The light fades gradually. The star simply blurs, slowly, into the surrounding space. Astronomers, when they speak of the star's surface, often mean a particular depth, a place where the gas becomes thick enough to block light. But this place is fuzzy. It moves. The star pulsates, slowly, breathing in and out over long periods of time. The surface is not a place. It is a region, a soft, glowing zone. If you could travel inward slowly, you would not feel any sudden change. The thin, almost empty space around the star would gradually become slightly thicker, slightly warmer, slightly more red. You would pass through wisps of expelled gas, material the star has lost into space, drifting outward in a slow, stellar wind. And then, eventually, you would be inside, not crushed, not burned, simply enveloped in a soft, warm, red haze. This is part of why we cannot easily measure the size of Stephenson 218. There is no single line to measure. Different parts of the atmosphere give different numbers. Different wavelengths of light show different depths. This is part of the mystery too, but we will come to that. For now, let us simply rest with this thought. A star so vast that its surface is more like fog than fire. A star so cool that you could approach it almost calmly. A star losing material into space, slowly, gently, building up clouds of dust and gas around itself that we cannot see except in the infrared. Despite all of this softness, all of this quiet, Stephenson 218 is not gentle in every way. Its sheer surface area is so vast that it shines with the brightness of roughly 440,000 suns. Some measurements suggest even more, a single star pouring out the light of nearly 500,000. Most of that light, of course, never reaches us. It is absorbed by dust along the way, scattered, reddened further. By the time anything from Stephenson 218 arrives at our eyes, or more accurately, at our infrared telescopes, it is a soft echo of what was sent. A vast star, mostly empty. A bright star, mostly hidden. A red giant, quiet in its final centuries, burning with the steady, patient glow of a long life ending. There is a quiet truth that astronomers have come to admit slowly over the last few years. We are not entirely sure how large Stephenson 218 really is. The number we use, 2,150 solar radii, comes from a single calculation done in 2012. It is a careful calculation. It uses real data, but it depends on something that, as it turns out, is not certain at all. It depends on the distance to the star. To know how big a star is, you must first know how far away it is. The reason is simple. A faint star, very far away, looks the same as a bright star, much closer. Without knowing the distance, you cannot know the true size. For Stephenson 218, the assumed distance is the distance to the Stephenson 2 cluster, about 19,000 light-years from Earth. This is the cluster the star sits in, or near. It seemed reasonable in 2012 to assume the star was a member of the cluster, and so the calculation used the cluster's distance. But there is a problem. When astronomers measured the speed at which Stephenson 218 is moving through space, they found something strange. Its velocity is different from the velocities of the other stars in the cluster, different by about 20 kilometers every second. This is a small number perhaps, but in astronomy it is a meaningful one. Stars in a cluster, born together from the same great cloud of gas, tend to move together. They share a common motion. They drift through the galaxy as a quiet family. If a star is moving noticeably differently from its supposed siblings, it may not be a sibling at all. It may simply be passing in front, a foreground star, closer to us, smaller than we thought. In 2020, a paper was published that examined this question. The authors looked at all the evidence. They considered the velocity. They considered the brightness. They considered the position. And they came to a careful, honest conclusion. The membership of Stephenson 218 in its cluster, they wrote, is doubtful. That single word, doubtful, changes everything. If Stephenson 218 is not in the cluster, it is probably closer to us. If it is closer, it is dimmer than we thought. If it is dimmer, it is smaller than we thought. The 2,150 solar radii becomes a number we can no longer trust. How much smaller? It is hard to say. Some estimates suggest the true size could be 1,000 solar radii. Some suggest a little more. Some suggest it could still be very large indeed, but not the largest, not the record holder. We do not yet know. There is another problem too, a more theoretical one. Astronomers, over many decades, have studied the way stars live and die. They have built models. They have observed thousands of red supergiants in our galaxy and in nearby galaxies. From this, they have learned that there seems to be an upper limit, a ceiling, on how bright a red supergiant can be. This ceiling is called the Humphreys-Davidson limit, after the two scientists who first noticed it in 1979. The limit corresponds roughly to a stellar radius of about 1,500 suns. Stars larger than this, the data suggests, simply do not last long. They become unstable. They lose mass too quickly. They cannot hold themselves together as red supergiants for long enough for us to observe many of them. Stephenson 218 at 2,150 solar radii sits well above this limit. This is not impossible. Nature does occasionally exceed its own usual rules, but it is suspicious. When a single measured object exceeds the expected limit by a wide margin, scientists tend to look again at the measurement, to check it, to question it. Both of these reasons, the cluster doubt and the theoretical ceiling, together suggest that the true size of Stephenson 218 is perhaps somewhat smaller than the number we have been using for over a decade, which, if true, means there may be other contenders for the title of largest known star. There is WOH G64, a red hypergiant in the Large Magellanic Cloud, a small companion galaxy of our own, about 163,000 light-years away. Its measured radius is about 1,540 suns, smaller than Stephenson 218 on paper. But the measurement of WOH G64 is much more confident. In 2024, astronomers used the Very Large Telescope Interferometer to take a direct image of it. The first time any star outside our own galaxy has been imaged in such detail. They could see its shape. They could see the cocoon of dust around it. They could measure it with care. WOH G64, some astronomers now argue, may be the largest star whose size we truly know. There is also MY Cephei and WY Velorum and VY Canis Majoris, once thought to be the largest, before Stephenson 218 took the title. There is even the famous Betelgeuse in the constellation Orion, which you can see with your own eyes on a winter night. And there is the cautionary tale of WOH G64. For many years, WOH G64 was believed to be the largest star known. Its radius was given as 1,700 suns. People made beautiful size comparison videos about it, wrote articles, drew diagrams. Then, in 2018, new measurements from the Gaia spacecraft showed that the distance to WOH G64 had been overestimated. The star was closer than we thought, and so it was much smaller than we thought. WOH G64 today is believed to have a radius of about 750 suns, comparable to Antares, smaller than Betelgeuse. The largest star in less than a decade became simply another supergiant. This is the quiet lesson at the heart of Stephenson 218. Not that it is or is not the largest, but that the question itself is harder than it sounds. The cosmos does not give up its measurements easily. Distance, brightness, temperature, dust, motion, all of these must be untangled carefully before we can speak with confidence. So, when we say largest star, we should perhaps say largest currently believed, or largest by one method of measurement, or largest for now. The truth is that we do not yet know which star in all the universe is the very largest. We may never know. There may be larger ones, hidden in dust we cannot see through, in galaxies too distant for our telescopes to resolve. And there is something quietly beautiful, perhaps, about a question that cannot be answered. The cosmos is large enough to keep its biggest things to itself, for now. Whatever its true size, Stephenson 218 has one thing in common with every other red supergiant we know of. It is dying. This is not a dramatic statement. It is simply what red supergiants are. They are the last great phase of a massive star's life, the long, slow exhalation before the end. By the time a star has grown to such enormous size, it has used up most of its fuel. The hydrogen at its core, which once burned for millions of years, is long gone. Now, deep at the heart of the star, helium is fusing into carbon. Carbon is fusing into oxygen. Oxygen is fusing into still heavier elements. Each of these stages is shorter than the one before it. A massive star spends about 90% of its life burning hydrogen, then perhaps 10% burning helium. Carbon fusion lasts only centuries, oxygen burning perhaps a year. The final stages, before the end, take only days, sometimes hours. We do not know precisely where Stephenson 218 is in this sequence. Its outer atmosphere tells us something, that it is cool, that it is bloated, that it is losing mass. Its inner core remains hidden. We can only model what we cannot see directly, but we know with reasonable confidence that the star is in the final 1% of its life. For a star of this size, that final 1% might be 10,000 years. It might be 100,000. It might, in some cases, be 1,000,000. By the standards of human civilization, this is an enormous span of time. By the standards of stars, which often live for 10 or 20 million years, it is a single soft breath. And then, at some quiet moment in the future, Stephenson 218 will end. The end of a massive star is one of the most violent events in the universe. Once iron begins to accumulate at the core, The star can no longer generate the energy it needs to hold itself up. Iron, unlike lighter elements, does not release energy when fused. It absorbs it. And so, in a single fraction of a second, the core can no longer support the immense weight of all the layers above it. The star falls. It falls inward. The outer layers, which had been gently pushed outward for millions of years, are no longer held up. They collapse toward the center at speeds approaching 1/4 of the speed of light. They strike the dense, ruined core. They rebound outward. They tear the star apart. This is a supernova. A supernova is, for a brief moment, brighter than an entire galaxy. The light of one dying star can outshine 100 billion other stars combined. It can be seen across the universe. But here, in the case of Stephenson 218, there is some uncertainty about exactly what will happen. Stars at the very upper end of the mass range, perhaps 30, 40, 50 times the mass of the Sun at birth, do not always explode in the way smaller, massive stars do. Sometimes the collapse is so total, so complete, that there is no rebound. There is no bright explosion to see. The star simply falls inward, almost silently, leaving behind a region of space where it used to be. What is left in those cases is a black hole, a small, dark, dense object, perhaps no wider than a city, sitting alone in the cosmos, a quiet relic of the giant that used to be. If Stephenson 218 explodes, and we are not certain it will, we will see a supernova in the constellation Scutum, brighter for a few weeks than any star in the night sky. It might be visible during the day. It might rival the moon. Astronomers anywhere on Earth at the time will look up and say, "At last." If Stephenson 218 instead collapses quietly, we may simply notice one day that the infrared source we have been studying is no longer there. The light from the surrounding cluster will continue. Other supergiants will burn on, but this one will have gone. There is something to sit with here. The light reaching us from Stephenson 218 tonight is 19,000 years old. When that light left the star, the last ice age had only just begun to retreat from northern Europe. There were no cities, no writing. Hunter-gatherers walked across plains that are now beneath the sea. In all those 19,000 years, as humans built civilizations and forgot civilizations, as we discovered fire and farming and finally infrared satellites, Stephenson 218 has been burning slowly, very far away. We do not know what it is doing right now. The light from now will not reach us for another 19,000 years. By the time we see what is happening tonight, most of us and our descendants will be long gone. For all we know, Stephenson 218 has already ended. The light from its death might be on its way. It might arrive next week, or in a century, or in 10,000 more years. We are, in a sense, watching a ghost, a star that may already be gone, sending us the gentle red light of a younger self. But here is another thought, a softer one. Whatever Stephenson 218 becomes, a black hole, a neutron star, a great expanding shell of glowing gas, its material will not be lost. The heavier elements forged in its core over its long life will be flung outward. Carbon, oxygen, iron, calcium, the atoms that will, one day, form new stars, new planets, perhaps, in distant epochs, new forms of life. We ourselves are made of dead stars. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was once at the center of a giant, much like Stephenson 2:18. Stars die. Their atoms drift outward. They cool. They gather. They condense. They become new things. The cosmos, in this way, is not a series of endings. It is a long, slow recycling. Each great death feeds another generation of light. When Stephenson 2:18 finally goes, quietly or in a burst of glory, it will scatter its centuries of fusion across the galaxy. And somewhere in the deep future, on some unknown world, the iron of its heart may form rivers. Its oxygen may form rain. A giant becomes a galaxy of small, ordinary things. The cosmos turns and turns. This is what stars are for. The night is quiet now. Somewhere in the constellation, Scutum, behind a veil of dust we cannot quite see through, a great red star is burning. Or perhaps not. Perhaps it has already ended. Perhaps its quiet light is, even now, slipping through the long dark between us, on its way. We cannot hold light. We can only receive it. Tonight, the light reaching us from Stephenson 2:18 began its journey 19,000 years ago. It crossed cold space. It passed dust and gas and other stars. It traveled longer than civilization has existed. And it ends, finally, here, gathered by an infrared telescope, translated into numbers, read by astronomers, carried by some long chain into this quiet moment with you. That is what a star is, in the end, a long, patient sending of light, a message from the past that arrives gently in the present, whether or not the sender is still there. We talk tonight about a star larger than our entire solar system, a star found by accident in the heat glow of an infrared sky, a star whose size we cannot quite agree on and may never be able to, a star whose end will come sometime in a way we cannot predict. We talked about how stars are born and how they die, about how the iron in our blood was forged in the heart of giants, about how the cosmos recycles its great things, slowly, over millions and billions of years. There is no need to remember any of it. The cosmos does not require us to know its details. It simply, patiently continues. The stars burn, they die, they scatter, they form again. We watch for the short time we are here. We try, with our gentle telescopes, to understand, and then we sleep. If you are still awake, that is all right. The night is long, and there is no hurry. If you are drifting toward sleep, even better. The cosmos keeps watch. The light is on its way. Sleep well, and good night.